Sonos' mission is to fill every home with music while providing a seamless user experience. One of the features that promotes this is voice integration.
When you use a phone to control Sonos, it's inherently personalized since it lets you pick music from your own playlists. What we want to achieve is a similar level of personalization in voice control.
Our target user is someone who shares a smart speaker with other people, but also wants seamless voice control that's catered to him or her. So essentially, we wanted to explore the question: what could you do if your speaker knows who you are? We hence created a system that lets smart speakers distinguish between multiple users based on voice, and voice only.
In order for our system to identify different users, each user has to give it some voice samples. We then use these samples to train a classifier that saves a unique voice profile for each user, which allows us to do very cool stuff like this.
Hey Sonos, could you play my playlist, please?
Okay, Emilien, playing your playlist.
Hey Sonos, I like jazz.
Got it, Aga. I added jazz to your list of tastes.
Hey Sonos, could you play something I like?
Okay, Aga, playing something you like.
Hey Sonos, can you play my playlist now?
Okay, Alvin, playing your playlist.
Our design has three major steps. In the first step, which is digital signal processing, we have users speaking commands into a microphone, so we want to clean up that audio and output data as a vector of features for the machine learning step. To do this, we first do some noise reduction. We're using a gentle bandpass filter. It attenuates frequencies outside the range of normal speech, which we've estimated to be about 300 to 3000 hertz. Once we've cleaned up the signal, we can calculate the mel-frequency cepstral coefficients, which represent the power spectrum of the audio across a special pitch scale called the mel scale, since the mel scale represents perceived pitch rather than absolute pitch, which makes it better for applications like speech recognition.
The extracted features from the speech still must be classified to the right speaker. In order to do so, we implement several different machine learning approaches to see which one would be the most suited to our purpose. We ended up using an LSTM neural network that can train on about 10 samples and have an accuracy of more than 90% for 5 different speakers. Our tests were done using a public dataset of text-independent recorded voice samples. The real-life trials were slightly below that accuracy level sadly, even with our signal preprocessing, probably because ambient noise and the similarity of our voices.
For the integration, we implemented 2 use cases which highlight the capabilities of our system: play my playlist and play something I like. After receiving the username from our model and the commands from the Google Search Speech API, a server queries the local database for soundtracks and then plays it to the connected speaker.
We didn't get the chance to implement our system on the Sonos API, but Sonos integration could open up some unique features for Sonos customers. For example, households with Sonos often have a speaker in each room, so they could say something like, Sonos, set my alarm for 9 a.m.
Okay, Alvin, the Sonos in your room will wake you up at 9 a.m.
A speaker that recognizes your voice among multiple users can have an important role in a seamless smart speaker experience. Any user wanting a more personalized voice control experience would appreciate it. It's certainly something that I would like.